Hi. Till now, we have developed many small projects in VHDL and integrated them on FPGA board as well. Now, from this session, we will develop little complex VHDL design, and we will develop this using multiple VHDL modules. We are developing a UART module with transmitter and receiver with flexible baud rate. In this session, we will understand the idea behind the UART module, and then from the next session, we will start developing it in multiple parts. Like one part is baud clock generator, one part is transmitter, one part is receiver, one part is serializer, like that. And we will also write test benches to test our designs. So this is the block diagram of a simple UART module. In the left hand side, we have our UART transmitter, for example, our PC, which is sending data. So you see this box here. Suppose this is your PC, and this small box here is your UART port or serial port in your PC. Now, in this right hand side, we have that same UART port or serial port. But now this is from your FPGA board. So you will see this serial port in your FPGA board. So we will get the data at this port, and then this data will be processed with the finite state machine in FPGA. We will talk about this finite state machine system sometime later. So this UART port from PC sending serial data, and this UART port at the FPGA port is receiving that serial data through this data lines. And once this UART receiver receives a valid character, then it will pass this data to this finite state machine. So this state machine will detect the character, and suppose it is again sending it back to the PC. Means now this UART port from the FPGA will act as a transmitter and PC will act as a receiver, and the data will flow through this data line. So it is a kind of a loop back application what we are designing. So we will design the system in VHDL, and then we will simulate it on Model Sim Simulator. Now, because this design is complex, so we will break down this in the individual module, and we will also design and test them individually. Like we will break down this UART transmitter into serializer and baud clock generator. We will separately design this state machine. We will split UART receiver into shift register and baud clock generator, etc. So there will be multiple modules we will be designing for this project. Okay, so let's talk about the UART transmitter first and see how we will design this. So here we are break down our UART transmitter into these two modules. This first block is a serializer block. So what it will do that it will convert 8-bit parallel data into serial data so that they can transmit over a single bit data line, because UART is a serial communication protocol and data can only transfer one by one. So we need this serializer to convert input 8-bit data into serial single bit stream. So we will write a VHDL code for this serializer. You can see this serializer has three inputs: DIN, load, and shift enable. And it has one output, DOut. Now DOut is a serial output, so it is single bit output. But DIN is a parallel data, and say it is 8-bit. However, it can have any length, like it can be 4-bit or 10-bit or 16-bit, etc. Now this load input. So it will be asserted whenever we have a valid data at this input port DIN. Means whenever this load signal is asserted, our parallel data present at this DIN port will be captured by this serializer. Now we have this additional input as well. This is shift enable, and this is very important for UART communication, because we cannot send this serial data which is coming out from this DOut port at any speed or at any bit rate. we need to be very careful that when the serial data will transfer to the transmission line, means we need to decide that when exactly we need to get serial data output. And for that, we need this shift enable pin. This shift enable pin will tell the exact time when your bit data should be shifted out from this serializer. We need this stringent timings because RS-232 protocol, which is used by this UART system, means your transmitter and your receiver has some very specific bit rate. So we need to make sure that all the transmissions and the reception must follow these supported bit rates. So this shift enable pin will control all these things for us. Do not worry, we will see that how it happens and how it works. And we will design this as well. But in brief, we have this second module here, and this module will generate this shift enable functioning in our design. We will call this Baud clock generator, and its output will be used as a shift enable pin for this serializer. Means you can say that this Baud clock output is connected to this shift enable pin of this serializer in our UART module, but we will design them as a separate units. Means we need to design this baud clock output to synchronize with very specific baud rate because it will drive the shifting operation of this serializer. So it will generate the pulses to shift out data based on very specific timing control, which we will call 1 bit period. So this is just high level. We will design it in VHDL little later. So we can see that this baud clock generator has start input and ready output, and of course baud clock output. Now what this start input will do. To understand this, let's see what this baud clock generator is doing. So it will generating pulses to allow the serializer to shift data to the output one by one and at very specific time bit period. Now suppose we have 8 bits at this input of serializer. Means we need 8 pulses to shift 8 bit of data, right? So this start input will tell that exactly when these pulses should start. Means for our example of 8-bit data, this baud clock generator will generate 8 pulses after this start input is asserted. Now we have one additional put, and that is output ready. Once this baud clock generator generates 8 pulses for our serializer, then it stops generating more pulses because we do not need them after data transfer is complete, right? So once this 8 pulse generation is completed, this ready output will be high. This means that our 8-bit data is transmitted and we are ready for transmitting the next data. And for this time, our baud clock generator will stop generating any pulses until next start signal is asserted. Means after ready signal is high, it will wait for this start signal. And when this start signal is asserted, this baud clock generator will repeat the steps, means it will generate 8 pulses to shift 8-bit data once again. And for that time, this ready output will be low. And once it completes 8 pulses and the 8-bit data is transmitted, then this ready output will be high again. Okay, so this is our UART transmitter module. And next will be UART receiver module. So let's see this in the next slide. So this is the block diagram of UART receiver. Your input data will come through this RX input. Now this input will pass through this synchronizer and you will get D in as an input. Now we need this synchronizer because we can get this RX input at any point of time. Means this input is asynchronous to the internal clock of FPGA board. So if you use this RX signal without this synchronizer, we can have stability problems in our designs, which is not good for a reliable design, right? So to avoid these issues, we will convert this asynchronous signals into a synchronous signals. So we have this synchronizer in between, and the output of this synchronizer is exactly same as this RX signal, but it is delayed by some clock pulses. Means this DIN has the same data as the RX signal, but it is now synchronized with the FPGA clock frequency. And we will use this DIN as a data input to our UART receiver instead of this RX input. Okay. Next, we will move this DIN signal into a shift register. Why? Because this DIN signal is a serial data which is received over the single bit transmission channel. And to recover the data, we need to convert this serial data into parallel data. So this shift register module will capture the serial data and then it will convert it into 8-bit output data, which is D out here. So this is our shift register, which will convert serial data into parallel data, right? Now you will see that this serial data is also connected to this start bit detector module as well. And what it will do that it will detect the signal whenever a new message or a new data is received by this UART receiver. Now there are some protocol standards of RS-232 protocol. And one important standard is that when RS-232 is ideal, means when it is not transferring any data, then this signal remains at logical high. And when data transmission is ready, then the first bit will be always logical 0. Means when data is not transferring, we have logical high. And when data is ready to transmit, then the first bit will be logical low. So simply, we will look for logical 0 to detect if any data is transmitting or not. Means we will look for the falling edge of this DIN signal. And when this falling edge is detected after the ideal state, we will say that there is some data is transferring. Means we detect a start bit through this start bit detector module. And once this start bit is detected, it will trigger this Baud clock generator. So this is a separate Baud clock generator module. We discussed this in the last slide as well for UART transmitter section. So this Baud clock generator will generate similar pulses to drive this shift register, and it will generate pulses based on the number of input bits. Like we have this RX port here or DIN port here. And this Baud clock is connected to this shift enable pin of this shift register, just like it is connected to the serializer in UART transmitter section. So each time this Baud clock pulse is given, this DIN input will shift 1 bit into the shift register. So if you want to capture 8 bits, you required 8 pulses. And at each pulse, this shift register will capture 1 bit from this DIN input. And once you capture all the 8 bits, you will get 8-bit parallel data output to this output port D out. So that's complete our UART receiver module as well. In the next session, we will quickly brief RS-232 protocol, and then we will design it and test it in VHDL with real practical and simulation. So stay tuned for the updates. If you did not subscribe till now, then please do subscribe to learn and grow community for regular updates. If this video is informative, then please like this video, comment on video, and don't forget to share. Thank you for watching.